Hello. In this video, we're going to look at Chapter 7, and it starts with integration by parts, which is a new technique for doing integrals we haven't been able to do so far. So let's get started. So you recall the product rule from Calc 1. What we're going to do is take the product rule and rearrange it and see if we can get a formula that'll help us solve some integrals we haven't been able to do yet. So whenever you have a derivative on one side and you take the integral, the derivative and the integral cancel. So if we take the integral of both sides, it cancels the derivative on this side. So we're left with just f of x, g of x. Over here, we just take the integral of this whole thing, tack on a dx, just for symbols' sake, and we can distribute integrals through plus signs. And then what we can do is rearrange it. So what I did to rearrange this, I subtracted this from both sides and then just flipped sides of the equation to get this. So this formula is a rewriting of the product rule. It'll let us solve integrals of this form. A function times the derivative of another function, dx. And it'll end up looking like this. And that's called integration by parts. So here's the official version of the formula. You don't have to know the official version because we are going to come up with a slightly easier version to remember. But this is basically what it says, right? If we have this integral of this form, we will solve it using this if it can be solved. Not every integral can be solved. And what we're going to do is we're going to simplify the notation to make it easier to remember. So we're just going to let u be f of x. V is going to be g of x. And then du, f prime of x, and dv, g prime of x. So we're just taking the derivative of these. It's called implicit differentiation and differentials that you studied in Calc 1. And the idea is you're just taking the derivative of both sides with respect to their own variable. So the derivative of u with respect to u is du. The derivative of f of x with respect to x is f prime of x dx. And then we just take all of these values and plug them into here, and we come up with this. So this thing at the bottom is what we're going to use. It's much easier to remember than this up top. All right, let's see how this works. So let me back up one sec here. If you look at it, on the left side, you have a u dv on the left side. So we have to choose u and then choose dv. What normally happens is once we choose u, everything else in the integrand we just lump together as dv. So we make this little table where u gets written here, dv gets written here. Then we take the derivative to find du, and then we integrate dv to find v. Once we have all four parts, we plug them into the formula, the uv formula, and then we solve it if we can. All right, so let's see how to do that. So here we have three different parts, an x, an e to the x, and a dx. So one of these parts is going to be what we call u, and the other two parts we're going to lump together. So when we want to choose which one is u and which one is dv, the rule of thumb is to choose u so that du is a simpler function than u was to begin with. So when we have this integral, x e to the x dx, we could choose u to be x. And if we do that, then the differential is du equals dx. Or we can choose u to be the other part here, e to the x. And its differential is du equals e to the x dx. So you can see that if we choose e to the x, then e to the x dx is definitely not simpler. It's the same. And so if we choose x, we have dx. So it turns out dx is simpler, right? There's a part missing. compared to e to the x dx. So we want to choose u equals x because dx is simpler than x. So simpler here does not mean a technical mathematical term. It just means easier to work with. We're just looking for things that we can solve more easily. If you look at the formula, that should make sense. Because we're going to have a u here and a u here. So if we plug x's in there, that's fine. Here's an x, that's fine. It doesn't do anything. Here's where we want to make it simpler. If we have a dx here, the integral of v du is going to be much easier to do than if it were more complicated. So we choose u equals x, dv is e to the x dx. And the way this table works, take the derivative to get du. To get v, take the integral. So the integral of this is just e to the x. You don't need to add a plus c here. When you get your final answer, just tack a plus c at the very end. Some of the examples in the book and in the homework keep track of all those constants. You never have to keep track of the constants. So even if that's what's going on in the book or what's going on in the examples, you don't have to do it. It's much easier to just wait till the very end and tack on a constant. So we plug everything into our formula. So the left side, we already know what the left side looks like. That's why we chose u and dv the way they are. And then we have uv, so x times e to the x goes here, minus the integral of v du. V is e to the x. Du is dx. So it's just x e to the x minus the integral of e to the x dx. We already know how to do this integral. It's just e to the x. So your answer is x e to the x minus e to the x. Tack on a plus c. And you can factor it if you want. But I'm not requiring any further steps than just as soon as you do the integral, as soon as you tack on the plus c, simplify any like obvious constants, like if there's two negatives, just make the whole thing positive or something, and you'll be done. So that's the answer. All right, let's do another one. And let's see what some other integration by parts problems look like. All right, so we want to find the integral of ln of x dx. Here we only have two pieces, two parts, not three. And we can't choose u as dx, so we choose u just to be ln of x. And if you're not sure why that happens, go ahead and try it and write it out and try to do the integral. You'll see that you can't do it because it just doesn't make any sense. So we're just choosing u to be ln of x, and let's see what happens. So we make our table. So u is ln of x, dv is dx. Derivative of ln of x is 1 over x dx. Integral of dx is just x. And if you're not sure why that is, remember this is just 1 times dx, and the integral of 1 is x. You just don't write 1s when that's the only coefficient. We can plug all of this into the formula to get this. So u was ln of x, dv was dx, right? That's what we started with. Here, u is ln of x. I switched them just to make it easier to read. You don't want to write ln of x, x, because it looks confusing. Just always put ln or cosine or whatever all the way to the right and pull polynomials to the left. So it's uv, but here u is actually ln of x, v is x. Integral v du, we know v is x, du is 1 over x dx. Looking at this, you might think, I don't know how to do that integral, but remember, you can simplify before you do the integrals. X times 1 over x is just 1, and the 1 just goes away. We don't write it. So it's x ln of x minus the integral of dx. And we've already seen that the integral of dx is just x. And don't forget to tack on plus c when you're all done. And that's it. So once you get the hang of this, it's really not too bad. So what you want to do here is pause the video and go back and do the first two examples without looking at your notes. Make sure you can do them. We will be using integration by parts a bunch this semester. So make sure you can do it without looking. And now we're going to look at the second part of the solution here for example 2, and that's checking answers. So I'm only going to check answers once in this video, but when you're doing the homework, on an indefinite integral, you should always check your answers with the derivative. On a definite integral, you should always check your answers on your calculator. There's no reason to get any of these wrong when you can check your answers. And if you're doing these and getting them wrong, you should be contacting me or going to tutoring or forming study groups or something. So let's take the derivative of the answer we just got and see if we get ln of x. So when we take the derivative, this is a product, so we have to use the product rule. Derivative of minus x is minus 1. Derivative of c is 0. When we do the product rule, x times the derivative of ln of x, which is 1 over x. Derivative of x is just 1. So just write everything out. The minus 1 stays there. The plus 0 just goes away. And you can see that this is going to further simplify. X times 1 over x goes away. Just becomes 1. We have to write it here because it's added, not multiplied. So we get 1 plus, this is just ln of x minus 1. And you'll see that the 1's on the end cancel. The 1 minus 1 cancels. And you're just left with ln of x, which is what we wanted. And when you take the derivative, you'll see the product rule working in reverse, because integration by parts is the reverse process of the product rule and the quotient rule, as you will see. It's used for both. So when you check your answer, you're either going to get a product rule or a quotient rule. And if you don't, then you did it wrong, because integration by parts must be used in those cases. All right, let's do another one. Here we have z squared e to the z dz, the integral of that. So this looks a lot like example 1 that we did, except you can see that there's a z squared instead of just a z. And we'll choose it the same way. We want u to be z squared because it gets simpler. So the derivative of z squared is going to be 2z dz, and the exponent is going down, and that's what we want. We want lower exponents. That's what we consider to be simpler in this sort of situation. So if u is z squared, then dv has to be e to the z dz, right? It's the rest of the, right? So this is our u. This whole thing is our dv. So we already know the derivative of this is 2z dz. We already know the integral of this is just e to the z, right? We saw that in example 1. Now we plug everything into the formula. So integral of v du, integral of u dv is u v minus the integral of v. So here's v. I put it in the middle. Du is 2z dz, 2z dz. The order doesn't matter when you have multiplication. So feel free to rearrange the order. You almost have to do it because if there are constants, you want to pull them to the front. So here, this 2 is a constant, so we want it out of the integral. That's definitely a habit that you should have gotten into in Calc 1, and if you didn't, you need to start doing it now. Anytime you have a constant inside a derivative, you want to pull it to the front. It's guaranteed to be easier. Now from this step, we're done with this. We're done with this too. This integral here is exactly what we saw in example 1. So you just plug in the answer. If you remember the answer, you can just plug it in. If you don't remember it, then you'd have to do integration by parts again, just like we did in example 1. So you're allowed to memorize integrals if you want to. Unless I specifically say, show every step of the calculation, I don't mind if you memorize integrals. And now that we have this, we just distribute the 2, and we're done. tack on a plus c when you're all done. Like I said, you can wait till the last step to tack on a plus c. I'm not requiring it for the intermediate steps. And that's your answer. And you could check this answer by taking the derivative, and you will see that it does come up with the original problem. But I'm not going to do the check step. That's something you can do on your own. All right, let's keep going. Oh yeah, last thing. We had to do integration by parts twice, right? Once here, and then example 1 was another instance of integration by parts. So there's theoretically no limit on the number of times that you do integration by parts in one problem. Usually you won't do more than 4. That would be about the limit. But theoretically, there's no limit. All right, now we're going to look at definite integrals. So definite integrals are very similar with one major difference. The only major difference is that when we use the integration by parts formula, you have that uv part. That has to be evaluated separately from the integral. Other than that, it's pretty much the same as what we've seen. So when we're setting up the integral, we're going to ignore this 0 and this 1/2. We don't care about it when we're setting it up. So we have arc cosine of x here and a dx. As before, as in example 2, we have to choose u equals arc cosine of x. That makes dv equals dx, the only remaining part. Derivative of arc cosine of x is this expression. The integral of dx is x. So our table is filled out. We can plug everything into the formula. So here's the integral, and that's going to be uv, right? So here's u. Again, I switched the order because you want trig functions and natural logs and arc trig functions on the right side. So this is u, this is v. We have to evaluate this from 0 to 1/2 minus the integral of v du. And I'm going to simplify it. So this is, if I said just set it up and do not continue, this is the next step. But in order to do this integral, I really want to keep simplifying. So I'm going to simplify it to this before I do the integral. So I took the two negatives, made it positive, and I multiplied x times this expression, and I put x in the numerator. Now what we can see is that we have an evaluation here, and we have an integral here. These cannot be done at the same time. So just do some side work, split it into two problems. For this example, I'm doing the evaluation of x arc cosine x first, and then I'm going to do the second part, integral, later. Okay, so here's what I'm trying to evaluate. X arc cosine x from 0 to 1/2. So you just plug in the 1/2, so we get 1/2 arc cosine of 1/2 minus 0 times arc cosine of 0. 0 times anything is 0, so this whole thing is going to go away. Arc cosine of 1/2 is pi over 3. So 1/2 times pi over 3 minus 0 is just pi over 6. So this whole expression just turns into pi over 6. So that's the first part. That's the uv part. Now we're going to do the integral of v du, right? Minus the integral of v du. And I had simplified it like this, right? I simplified it by taking the minus sign out. So this is just a u substitution, right? Because we can see that we have an x squared and an x. So this looks like the derivative of that. But I want to do 1 minus x squared as my u. Now, if you don't want to write u here because we used u earlier in the integration by parts, you can change the letter to t or w or z. Whatever letter you want to use is fine. If as long as you're not mixing up this u with the u from the integration by parts earlier, you can use whatever letter you want. If you start mixing them up, switch the letter to something else. I don't mind either way, though. So here we have u is 1 minus x squared So du is minus 2x, right? Take the derivative, minus 2x dx. We don't have a minus 2x dx here. We have an x dx. So you manipulate this until you get an x dx on the right, which means negative 1/2 du is what we're going to substitute in. So when we do the substitution, you substitute everything. So the limits of integration need to be substituted. So we plug 0 into this. So u is 1 minus 0 squared, this bottom limit. The top limit is 1 minus 1/2 squared. This becomes, so the x dx becomes negative 1/2 du. What's left over is a 1 over, and there is u, so it's 1 over square root of u. Next step, I'm going to simplify this whole thing. As usual, if there's a constant, I pull it to the front. So negative is considered a constant. The 1 over radical u, I'm going to write as u to the minus 1/2. And then you simplify the limits of integration. 1 minus 0 squared is 1. 1 minus 1/2 squared is 3/4. All right, so I'm ready to do the integral, but I really don't like this negative out front. So I'm going to use the rule that says if you switch the limits of integration, it flips the sign on the integrand. So I swap the 1 and the 3/4. I'm picking up a negative here, which will cancel with this negative. And then you just get u to the minus 1/2. You don't have to switch these things if you don't want to. But I really don't like having a lot of negatives inside evaluating integrals. It just adds a lot of confusion, and you really, if you can get rid of a negative, get rid of it. So this is a legal move, so we're going to do it. Well, this is an easy integral, right? It's just the power rule. So add 1 to the power, so negative 1/2 becomes 1. Divide by the new power, so dividing by 1/2 is the same as multiplying by 2. We're going to evaluate from 3/4 to 1, and the 1/2 stays out front. In the next step, this 1/2 and this 2 will cancel, so it just goes away. And then we just have 1 to the 1/2 minus 3/4 to the 1/2. Simplify it, and you just get 1 minus square root of 3 over 2. Now, this is the second part of this integration by parts that we did. So the final answer is what we got for this minus what we got for this. We're going to add them together because I had already simplified this, but this is just the first step when I plugged everything in. Right? These two negatives canceled, so we're going to add these. So it's pi over 6 here, plus 1 minus radical 3 over 2, and that's the answer. You're done. If you want to check your answer on a calculator, it's going to come out to 0.658. And if you want to do a bunch of algebra, you can further simplify it to this. It's up to you. Just a lot of times the answer keys write it like this. So perhaps you want to practice simplifying this, putting it in a different form and stuff like that. Okay, we got one more example to go. And the last example is about reduction formulas. So reduction formulas are a way that when you have an integral of a function to a power, that you can, there is a formula that instead of doing integration by parts, we're going to prove the formula with integration by parts, and then you can just use the formula. Again, if you want to memorize it, totally fine by me. There's lots and lots of integral formulas. There's only about 5 derivative formulas, but there's about 600 integral formulas. So there's a lot to know. Integrals are tougher than derivatives. So here's our reduction formula. The integral of sine to the nth power of x dx is negative 1 over n cosine of x sine to the n minus 1 power of x plus n minus 1 over n times the integral of sine to the n minus 2 power of x dx. Once we have this formula, we're going to evaluate this expression. So let's go ahead and prove this formula with integration by parts. Now looking at this, you might think I'm going to make sine nx u, I'm going to make this dv. It turns out if you do that, something bad happens. So instead, what we're going to do is we're going to take one of the signs in here and put it with this dx. And what's left over is sine to the n minus 1 dx. Right? So we're taking one of the signs and putting it here. And then all the rest of the signs are here. This is actually pretty easy to evaluate. The reason we did this is if you integrate just dx, you end up with an x here. And you can see in the formula that there's no x just floating around, which means you can't choose that. So the derivative of this is the power rule and the chain rule. This doesn't look like a chain rule, but it is. Sine to the n minus 1 of x is sine of x, and then that whole thing to the n minus 1 power. So the inside function here is sine of x. So bring the power down, lower the power by 1, and then multiply by the derivative of the inside function. The inside function here is sine of x. Derivative is cosine x. So you get this whole thing, dx. Here, we chose sine x dx as our dv. So the integral is negative cosine x, which can't beat that, right? That's a nice integral. Now we plug everything into our formula. So here's u, here's v. Again, I just switched them. The order does not matter. Minus the integral of v, and then this whole thing is du. Next up, you want to simplify. So what I did, n minus 1 is a constant. I pull it to the front. These two negatives will turn to a positive. And then this cosine and this cosine I multiply together to get a cosine squared. And then this remains unchanged. You can't change this. Now what we're going to do is we're going to use the trig identity. Cosine squared of x is 1 minus sine squared of x. We're going to take this cosine squared and replace it with a 1 minus sine squared of x. Then we're going to distribute. So I'm distributing the integral here, and I'm distributing on the inside. So 1 times sine to the n minus 2 of x dx is just this. Minus, distribute the integral, sine squared x times sine to the n minus 2. Add the powers, and you get sine to the nx dx. None of this other stuff changes. And what we see is that over here, here's a sine to the nth power x dx, and I have one on the left side. So I ended up with another copy of my original integral, and that's how we're going to solve this. So I distributed the right-hand side. All I did is distribute the n minus 1. So if you go back and look, here, what I did from this step to this step is the stuff inside the integral. Now I'm taking this thing on the outside of the integral and distributing it. So we get an n minus 1 times this one, and an n minus 1 times this one. So here is a n minus 1 integral sine n dx, and here's one of them. So here we have n minus 1 on this side and 1 on this side. So if I add n minus 1 times the integral sine x dx to both sides, it cancels over here. I'm adding n minus 1 of these things. So n minus 1 of something plus 1 of something is just n of those things. Now I divide by n, and I'm done. So divide by n, so it cancels on the left. We get negative. So negative of this divided by n is the same as multiplying by 1 over n. And then here's n minus 1. I divide by n, and I get an n in the denominator. And that's exactly the formula I was trying to prove. So make sure you can prove this formula. Any proofs that I do in the notes as examples could be on a test. I know it's a hard proof. Make sure you can do it. because it's a lot of good practice with integration by parts. Now, for part B, we're going to use what we just came up with to evaluate the integral. So here we have a definite integral. So it's from 0 to pi over 2. So this gets a 0 to pi over 2 on it. This integral gets a 0 to pi over 2 on it. N becomes 3. So any place I see an n, I replace it with a 3. So this n here is a 3. N minus 1 is 3 minus 1, which is 2. N minus 1 over n is 2 divided by 3. N minus 2, 3 minus 2 is 1. So I have to evaluate this and this. This is an easy integral, so I'm going to go ahead and just do everything at the same time. Right? This integral is just cosine of x. Right? I'm sorry, negative cosine of x. So it's just 2/3 times negative cosine of x from pi over 2 to 0. So that's not a hard integral to do. So I'm skipping that one step of Calc 1 that you should be able to do. All right, so let's see what happens. So we have negative 1/3 cosine of pi over 2 sine squared of pi over 2 minus negative 1/3 cosine of 0 sine squared of 0 plus 2/3. This integral is negative cosine of x pi over 2 minus negative cosine of 0. Again, the 2/3 was on the outside, so I kept it on the outside. Here, the 1/3 is on the inside, so it shows up twice. Now, what you might notice is that the first part of this formula has a cosine and a sine in it. The second part has a cosine and a sine. Well, cosine of pi over 2 is 0. Sine of 0 is 0, so sine squared of 0 is 0. This whole thing is going to be 0. This whole thing is going to be 0. This is not a coincidence. If your limits of integration are 0 to pi over 2 of a sine of x, both of these things will go away no matter what. And sine to the nth power of x. 0 to pi over 2, because this cosine and sine show up, you get 0 for cosine, you get 0 for sine. The whole thing goes away. Right? There's a 0. Boom, this whole thing's gone. Here's a 0. This whole thing's gone. And again, negative cosine of pi over 2 is 0. But here we're subtracting, not multiplying, so we have to keep track of it. So negative cosine of pi over 2 is 0. Minus negative cosine of 0, which is 1. So I have minus negative 1. So I'm going to have 2/3 times minus negative 1. Well, that's just 2/3 times 1, which is just 2/3. So this whole thing ends up a really interesting number, 2/3. So sine cubed from 0 to pi over 2 is just 2/3. All right. So that's how you do problems of this type. You have some homework like this, so make sure you're following along. This is also another good problem to be able to do without looking at the notes. So go ahead and try it without the notes. That's it for this video. If you have any questions, let me know. You can do the exercises in the book for extra practice. And of course, lots of online resources if you want to look at this stuff further. So if you have any questions, post on the discussion forum or shoot me an email or pop into tutoring. And I'll see you next video. Bye-bye.